remind me what a confidence interval is? Let's go back to 8.1, what we did last class that we were here. What is a confidence interval again? Nate?
How sure you are that the actual,
So it's an interval.
yeah, interval, how sure
A
you are
range.
that the actual,
Parameter.
huh?
The actual parameter.
Falls within that.
Exactly. So it's a range of values that we are certain confidence, whether a certain percentage of confidence, whether it be 90%, 95 is the most common if you remember. But it's a range of values and that we're pretty sure captures the population parameter. When I was looking at some of your quizzes from last class, the multiple choice part where it talked about the difference between a parameter and a statistics, quite a few guys got that wrong. So we really need to make sure when we get those back that we look at that and really truly understand the difference, okay? So let's talk about what it means specifically with proportions. So we're going to take, well, this is what we're going to be able to do today, okay? We're going to be able to construct and interpret a confidence interval specific to proportions. We're also going to do some work with some of the formulas. We're going to be able to determine a sample size that we need to collect in order to determine a level of confidence with a specified margin of error. And we'll talk about what that means. But we're basically going to be solving for n. We're going to do some math, some actual calculations today. It's just algebra. It's pretty basic. But as you know, we have square roots in our formulas and things, and so we'll have to look at that a little bit more closely. And then we're also going to talk about how a margin of error fluctuates and changes in size with sample size and level of confidence, which we kind of already talked about last class. But we're going to do an activity to start our morning, okay? I went out and got us some beads. I'm kind of excited about this. I would like for you guys to get into some groups of 4, so if you don't mind going ahead and picking up and moving desks are fine, but I'd like for you to go ahead and get into groups of 4, if that's possible. If we have a group of 3, that's fine, but no more than 4. And then I'm going to come around and give you a sample of beads, okay? So you're going to, I hope these don't drop all over the floor, but I'm going to try to put them very carefully on a flat desk. So whoever is your designated desk person, give me some room to put the beads. And you're going to count the red beads versus the non-red beads. Does that make sense? And you're going to find a sample proportion. Why would this be a sample? Because it's not the whole thing, right? I'm just doing a scoop. Do you agree? Okay. So we're going to do a sample of red beads. Okay. So you're going to do that, and then I want you to try to figure out how we could come up with a confidence interval. We're going to do 90% confidence. We should do 95 because 95 is the one that you know. You said you estimated it with a 2. Would you agree? So we'll do that. That's fine. We'll do 90 in maybe a little bit later and talk about the difference between 95 and 90. So let's do a 95. Go ahead and create one. And then I would like for you to actually graph your confidence interval up here. Okay? So remember, so you have from 0 to 0.35. I'm hoping no one gets above 0.35 because there's not that many red beads in here. There's 9 different colors. So I'm hoping that this is a good enough range. If I need to extend it, we will. But I want you to graph your confidence interval. So you're going to graph a line, and then the next group will graph above that, and so forth. So remember how we looked at that a little bit last time? Perfect. Okay. So go ahead, get in your groups, and I will come by and give you a scoop of beads. If you remember from last class, how do I create a confidence interval without a standard deviation or anything else like that? So what we're going to look at, and maybe we should actually create a 90 since, let's do 90. No, let's do 90 because that's what the activity asks us to do. So let's say whatever your p hat is, okay, this is obviously not yours. I would imagine that your p hat is a lot smaller. Would you agree? Okay. So pretend like this is the example p hat, okay? So how do we find a confidence interval for p? Well, let's make sure we check our conditions, okay? Is the sample size large enough? So you need to check those conditions. You need to check that n times p is greater than or equal to 10, or n times 1 minus p is greater than or equal to 10. The problem is we don't know what p is, so we're going to use p hat. Is that okay? All right. to check those conditions. Here is our standard deviation formula. Again, we don't know P, so we're going to use P hat. Is that okay? Then down here, I just wrote this over here. In practice, we don't know the value of P, so that's where we're going to use P hat. So here's our standard deviation formula, and you need to check your conditions. Now, there are a couple of conditions to check, if you remember. Not only greater than or equal to 10, but then we have the 10% condition as well. I will tell you that there are a total of, I believe it's 3,000. There were 3,000 bees, okay? So you can check your sample size to make sure it's less than 10% of the overall population. So I'd like for you to check those conditions first, based on your sample. We should all be about, I don't know, how much was this scoop? What was your sample sizes? About 300, around there? Yes, no, maybe so? Okay, so check that condition. So is that less than 10%? A little bit more, but it's about 10%, right? So we'll go with it, all right? I'm too big of a scoop. Darn, I should count it first. We'll pretend like it's okay. All right, so 10% condition, hopefully 309 is a little more. Not much. And then we're going to check the n times 1 minus p and n times p. Go ahead and check that now. Based on your p hat, is it greater than or equal to 10? Hopefully it is. Is it? So I know I originally told you 95 because we did that last time, and we estimated because it's within 2 standard deviations. But I want us to be more exact about our critical value. So let's actually do a 90% so we can look at what that means, okay? So I will tell you, well, check your conditions. We did that. These are just our, sorry, we know this. Critical value. So remember this formula for last time, okay? Here's your p hat. Do you agree? And then we can find our standard deviation of the statistic using our formula. It's called the standard error, not standard deviation when you use p hat. Just it's a vocabulary difference, okay? And it's not standard deviation, but standard error. And then the critical value, that's our z star, right? We're talking about normal distributions. I'm just going to write that here. And that's normal curve, which we know. So to find a 95% confidence interval, we use a critical value of 2. That's what we did before. I want us to actually figure out what it really would be. So take a second, if you don't mind, and you might want to write this down to help you figure out what the z-star should be for 90%, okay? And then we'll go ahead and graph these. But I want us to figure out how they got 1.96 instead of 2. 2 is an estimate. It's a rough thing. It's within 2 standard deviations. Where does 1.96 actually come from? Well, if we're trying to figure out a 95% confidence interval, don't you agree that's the middle 95%? Yeah? Which means how much is in each tail of the normal curve? About 2.5%. Do you agree? So the z-star is located here, okay? And how would I find the area not the area, what area is to the left of that right-hand value? Exactly. It's the 95% plus 1 of the tails. Do you agree? So that's 97.5%. How would I find a z-value associated with 97.5%? Inverse norm. Do you agree? So go ahead on your calculators and type inverse norm 0.975. And again, that includes 1 of the tails. So 95% confidence is associated with 0.975 area under the curve. And then because it's a z-value, what's the mean and standard deviation? 0 and 1. And tell me if you don't get 1.96. Okay? So that's how you find the critical values for different percentages. I want you to attempt with the people in your group now to figure out what the critical value would be associated with 90%. Okay? Same kind of idea, looking at your middle 90%, how much is in each tail, figure out what the critical value should be. All right, so we did a 90% these are 90% confidence intervals. What do you notice about, as we share through the class, what are you noticing about these? Okay, they vary a little bit, do you agree? But the widths are all about the same. And that kind of makes sense because your sample sizes were about the same. The standard deviations aren't going to be that different. It does, obviously, the standard error, I keep saying deviation, but you're using the p-hat, so it's really called the standard error. But your z-star was the same, right? So what you're adding and subtracting on either side of your point estimate, and I had you guys graph the point in the middle, which is your p-hat. Could you give me a rough estimate, looking at that, about what you think maybe the true proportion of reds would be? 0.09? 0.08? It's 0.1. 0.11, actually. So we captured it almost every time, except for one. You guys didn't capture 0.11. I thought you said it was 0.10 something. Right, so you guys did not capture 0.11. But most of the time we did, and as we went and did it more, that's what would happen, okay? We would, 90% of the time, we would capture it, right? What would happen if we changed it to 95% confidence? What would happen to those lines? They get longer. Because the more confident we are, the wider our confidence interval is. Do you agree? The more confident we are, the wider they become. The less confident we are, the smaller they become. I will tell you that very rarely do you ever go below 90%. Okay? It's usually 90, 95, and 99. So what I'd like us to do is kind of create a table of values for critical values of the most common ones. So these are ones that you can memorize if you want to, quite honestly. I might ask you on a quiz, what's the critical value? Critical value means Z-star, okay? What's the critical value associated with 92%? Could you do that? So now you know the process, right? You put your 92% in the middle and you figure out what's on each tail and do inverse norm. So we know how to find it, but you don't have to find it every time because critical values come up so often. So when we talk about critical values, let's just kind of, and you can, again, these can be just simply memorized. So we talk about 90%, which one did you guys get? 1.645. And I kind of came around and told each of your groups that that's really the rounding place that's kind of typical, okay? What about 95%? What did we get with that one? We just did it as a class example. 1.96. And then I'd like for us to go ahead and find the one that's associated with 99%. Take a second and figure out, using the properties that you know how, and let's come up with the critical value associated. Once we found them, you can just use these if you want to memorize them, that's fine. If you're not a memorizing person, you want to find it each time, it takes about a minute. So it's not that bad. So 2.576 is what we round to typically, okay? Typically it's 3 decimal places, except the 95%, I don't know why they just rounded it. Okay. So this is what is acceptable, typically what you'll see in terms of values and what we would round to. So again, I'm never going to ask you to calculate this each time. You don't have to show that work or anything. These can be memorized. The only time I would want to see work if I asked you specifically to show it or to find an odd one. Okay, like a 92% or something like that. Any questions so far? All right, we're good. So we already know how to find a critical value. We've already done that. So, and we've already done this formula. So we're moving right along. I claim that 11% of the beads, everybody has their own confidence interval written down, correct? For their group? Good. I want you to comment on your claim, on my claim. I claim that there's 11% of the beads are red. Look at your interval, and let's interpret that. What do we think is true about my claim? Is my claim, can we say that we agree with it, disagree with it? How would I write that as a sentence, okay? So think about your interval, and how would I interpret that interval based on this claim? Think about the wording that you're going to use. So let's tell me what you got. So I am 90% confident that it's true or not true is really what you're going to say. Okay? So most of us captured the 11%. Would you agree? One group came close but didn't actually capture it. And that's unusual for the small group, but that's okay. It happens. Statistics, nothing's perfect. So we would say that, for the most part, this is kind of what we would say. Okay, not kind of, this is what we would say. Yes. You're 90% confident that from captures the actual, that's perfectly fine too. Okay? So we have to put our confidence interval, our confidence level in there, which in this case is 90%. We have to say something about capturing the parameter. Remember that the parameter is the actual population proportion. So you can say parameter, you can say true proportion. I've seen it both ways. Of red beads, we're going to put the claim in there, and you have to say why. Because it falls within my confidence interval, falls within the range. You can use the numbers there if you wanted, like Bryce was saying. Now the group that didn't, you would say, I'm 90% confident that the true proportion of red beads is not 11%, because it does not fall within my confidence interval, is what you would say. Okay? So any questions about that? Interpret is important. I will ask you to do that on your quiz next week. Fair enough? Remember, that quiz was on quarter 3. All right, excellent. So, and this is what they did based on the proportion that they came up with, which is way too high, but that's fine. And in their case, they gave us, they were trying to, the claim was different. Don't worry too much about this. We've had a different proportion, right? So if this was theirs, what would you say about this interval? Does it capture the proportion of our beads? Definitely does not, right? So we would say this is the range that captures the true proportion. Since the interval is not, we have reason to doubt the claim, right? We think that the claim is false. All right, so let's move on to sample size, okay? So we know how to find a we know how to find a critical value, a Z star. We know how to find a standard error. We know how to find a confidence interval for proportions. Let's figure out how to find a sample size that would be necessary, okay? So, margin of error. And I wrote this over here, and so I forget who it was. Like, what's that? Oh, Tavis was like, what's that mean? That just stands for margin of error, okay? It is actually what you are adding and subtracting on either side of your point estimate of your. Sorry. What you're adding or subtracting to kind of get the width, so to speak, of your confidence interval. That comes up. I've seen that question before. What's the width of your confidence interval? Well, isn't it just twice the margin of error? Would you agree with that? The width? Okay. So that's something to consider as well. We're going to be looking at this, and we're going to be able to, using this margin of error formula, to actually be solving for the sample size. Okay? So we'd have to have all the other pieces of information in order to be able to do that. And let's see if we can do an example. Okay? Now, what if we don't have p hat? We actually, so we're trying to figure out within. For example, when we look at our example that we're going to do in a minute, we want to fall within a certain margin of error. Within, like, if you think about, you ever see those polls for like the election where it's on the TV and it says plus point or plus or minus 0.03 or something? I don't know what the percentages are. That's your margin of error. Okay. So what if we didn't know what p hat was? Well, if we use 0.5 as a guess for p hat, that's going to be the largest possible margin of error that can exist. Can someone tell me why that would make sense? We're trying to think about the largest possible margin of error. Why would a p hat of 0.5 give that to me? Well, it has to do with what's in the numerator of our standard error. 0.5 times 0.5 is 0.25, right? What would 0.3 times 0.7 be? Less than that. What would 0.2 times 0.8 be? Less than that. What would 0.3 times 0.7 be? I already did that one, didn't I? Anyway, you get the idea. The largest possible is 0.5 times 0.5. Kind of what you were saying, I think. All right? So that's why we can kind of take a guess, if we had to, if we weren't told what p hat was, we're going to use 0.5 as the worst case scenario, if I want to say it that way. Okay? So let's try an example. I'm going to pause this for a minute. I want you to read this, pull out key pieces of information, and let's see if we can't set up a formula or set up an inequality to solve. What are some key pieces of information? So 3%, let's start with that one. So 3%, what is 3%? It's the margin of error. Do you agree with that? Okay, so let's just write the things down that we know. So we have a margin of error of 0.03. Good, keep going. What's another key piece of information? The 95% confidence interval. The 95% is associated with what z star value. And why do I want to care about a z star? Because that's part of my margin of error formula, isn't it? So what is a z star that's associated with 95%? Okay, so we know that. So we're going to kind of write that down. Good. What else do I need? Well, let's write down our margin of error formula. Our margin of error formula is z star times the standard error, which is going to be p hat times 1 minus p hat all over n. So we're solving for n. The question's asking what size sample do I need. Do you agree? From just the margin of error. Yeah. What else do I need? What information is missing? The p hat. So I'm not given a p hat, so we're going to do the worst case scenario here and plug in a 0.5. Okay? So we're going to say, okay, and since we want it to be within 3%, we want 3% to be the maximum. Did you agree? So we have 1.96, and then we have 0.5 times 0.5, because 1 minus 0.5 is still 0.5, and we're solving for n. Do you agree? We just have to solve this. How do I solve this for n? Think back to algebra. This is math. This is exciting. You don't do a lot of calculations in this class. Divide by, well, 1.96. Okay. Algebraically, what do I do next? Square both sides. Okay, so far, algebraically. Questions? What do I do next? Multiply by n and divide by. Are we algebraically at a point where I can just do this? You guys let me know if I need to show more work. Is that okay? Basically, you're multiplying both sides by n and then dividing both sides by 0.03. Divided by 1.96 quantity squared. That helps. That way. What is it? Go ahead and find it. If you do this one step at a time and use rounded values that you get early on, your answer will be incorrect. That's really important. So either store the values on your calculator if you're comfortable with that. Just keep it like this and put the final answer in your calculator all at once is fine. Use the previous answer, those kind of ideas, but don't ever round with this calculation until the very end. Okay? All right, so it looks to me something along those lines. Oh, Mike. Are you sure? Okay, Nick. It should be the other way around. When I said that initially, it has to be within. So I think I've done this backwards the whole time. Oh, so it has to be greater than because it's within, right? So that's the largest it could be, 0.03. I drew that backwards. I said it, and then I was just like, I'm just going to keep going. But yeah, it's the other way around. Because 0.03 has to be the largest possible, so it's within, right? So that's why 0.03 has to be as big. So let me just draw this accurately. That is the correct, really, way to write it. Now, we need to think about this as a sample size, okay? We are counting beads, or we are asking people questions. We're not asking someone's left foot a question, or we're not counting as part of a bead, so we can't really leave our answer this way. We have to give it as a whole number, okay? So what should the whole number be? Mike? Yeah. Because of the greater than scenario, we have, no matter what this is, I don't care if it's 0.0111, it has to be greater than that next number. So you're going to say that the sample size is needed is at least this. At least, right? You can have a larger one, but at least this. So it's the smallest sample size needed to achieve that margin of error within 3%. Do you agree? So is the needed sample size. Is that okay? You okay why we had to round up? Okay. I believe that this work is shown for you here. See it? So they should hopefully get the same thing. And they did, and they rounded up, I hope, at some point. I think they might have done on the next page. Oh, they did. All right, whatever. It should be, like I said, 1,068. Okay, needed sample size. All right, so we have some time. I was supposed to talk about your quizzes for the last half of class. I didn't get those graded. So since you have time in class, I'm going to give you some time to grab a textbook and go ahead and work on any assignments that you might need for this chapter, whether it be 8.1 or 8.2. You should kind of be able to get most of those problems done in class today. We're going to move on to means next class. And remember that the quiz is we're going to take two quizzes, one on means, one on proportions, other way around, one on proportions, then one on means, and those will be next week. So I will see you guys, what's today, Thursday? Next Tuesday, right? We'll do means, and then your quiz will be next, hang on, I see Monday. I see you Monday. So your quizzes will be, the proportions quiz will be Wednesday, and your means quiz will be Friday of next week. Okay?